Hello, I'm Bobby Davis from the University of Minnesota. Here I'm going to be presenting work with my co-authors Ioannis Karamouzas from Clemson University and my advisor Stephen J. Guy. So we're focused on the problem of mobile robot local collision avoidance. That is, given a robot in some environment with a series of dynamic obstacles around it and some goal point the robot is trying to reach, what control should the robot be taking right now? So we seek a framework that generates anticipatory, collision-free controls in real time and that can be generalized to a variety of different dynamics models. So an example, here's the result of our system on 6 different dynamics models in the same sort of scenario. So here we have a velocity-controlled robot, a differential drive robot, and a car-like robot, along with the second-order models for each. In this scenario, there's a large number of linear velocity obstacles that the robot must avoid while navigating between a series of waypoints. As you can see, the robots are generating smooth trajectories that are able to avoid collisions while making good progress along these series of waymarks. So formally, the problem we're solving is, given a robot including a start state and a dynamics model, a set of obstacles including their expected trajectories, and a goal position, either given by a user or some higher level planner, we want to find a single valid control that avoids collisions and approaches the goal quickly. By single valid control, we mean a single control that we're going to pretend we're going to execute over a long period of time. Note that even though a single control won't be able to reach the goal, because we're going to be able to replan quickly, we'll be able to generate trajectories that actually do reach the goal. So we're going to do this in an optimization-based fashion. So we're going to minimize the sum of 2 different cost functions, one associated with the distance to the goal, and one associated with any collision costs. So the distance to the goal, we're simply going to propagate ourselves forward, the robot forward, by t goal seconds, and then measure the distance to the goal. For the collision cost, we're going to propagate both the robot and the obstacles along their predicted trajectories, and then determine the first point in time for which they collide. In this case, that point is about 2.7 seconds. Once we add together these 2 cost functions, we can compute this final graph of the cost over control space. As we can see here, the robot is going to be in collision if it moves forward and turns to the right, or if it moves backwards and turns to the left. This background is just the goal cost. So there are some complexities associated with this cost function. So specifically, we can see that moving from a colliding control to a non-colliding control results in a large jump in cost. And the second issue that comes up is that time to collision is generally not solvable in closed form. However, we can solve the sharp discontinuity by using subgradient descent as opposed to normal gradient descent, and we can solve for the gradient of the TTC cost by using implicit differentiation. Please see the paper for a full discussion of our solutions to both of these problems. Here we see the path generated by our method for the previous scenario. As can be seen, the robot is able to just gracefully pass just by the collision while making good progress towards the goal. While our optimizer is given a set of expected obstacle trajectories, the obstacles might not actually follow those trajectories in execution. In this scenario, we see a set of differential drive obstacles, each following a sinusoidal path. The robot is only given information about the current linear and rotational velocities of each obstacles, but is still able to smoothly avoid the obstacles while making good progress through the set of goal waypoints. Similarly, we can extend to multi-robot scenarios where each robot is planning separately. Note that to get this working, each robot updates the control using momentum such that the implicit coordination between the agents is stable. Then we can apply this to real robots. Here we can see 3 differential drive robots smoothly implicitly coordinating between each other and navigating to their goals without running into each other. In this final scenario, we have a chasing agent following a lead obstacle. However, there's a slower obstacle in the middle. Our agent is able to smoothly navigate around the slower obstacle and merge in between the two to safely follow the lead obstacle. For more information on our work, please see me in the live discussion section. And for more videos and reference code for our work, please see our website.